Hi, I'm Kay, and as Elise said, I'll be talking about a new distributed scheduler for Spark. In this talk, I'll start by talking about the Spark scheduling bottleneck. All of the Spark schedulers today rely on a centralized architecture, and I'll talk about why that's a problem, and also how you can diagnose if the scheduler is the bottleneck in your cluster. Next, I'll present Sparrow, which is a distributed scheduler for Spark that doesn't rely on any shared state. It's fully distributed, so all of the schedulers operate independently, making it fault tolerant, and it can also support very high scheduling throughput. Finally, I'll show some results. I'll demonstrate that Sparrow performs well using a TPC-H workload on a 100-machine cluster. And also, by the way, I just want to say quickly, I see a bunch of people taking photos of the slides, and all of the slides are available online. If not already, they will be soon. So you don't need to take cell phone photos, although you're welcome to. So first, let's talk a little bit about what Spark looks like today. So if you're running a Spark application, say Shark, for instance, and you have a bunch of worker machines, these are the machines that are actually running the tasks for the workload. All of the workers are coordinated by the Spark context, which is this centrally located component that does a couple of different things. First of all, it does query compilation. This is what Patrick talked about, taking the user's query and compiling it down into a DAG of stages. The Spark context also handles scheduling, so it assigns all of the tasks in these stages to worker machines. And finally, it handles storage. It keeps track of all of the RDDs that your application is using and where they're located. So if you have a bunch of different users that are all trying to access the same data and all run on these same set of workers, all of those users are funneled through this one Spark context, through this one centralized component. And in many clusters today, this can start to become a bottleneck. And in particular, the scheduling will become a bottleneck. There's two different trends in today's clusters that exacerbate this problem. The first trend is that jobs are getting shorter and shorter. If we look at these large-scale data analytics frameworks over the last 10 years or so, in the beginning, the typical job was quite long. This was a MapReduce job that would take many hours to complete. But ever since the very beginning, there's been this big drive to push down job latencies. There's been innovation in improving the query language with things like Hive. Things like Dremel used improved data layouts and more parallelism to drive down job latencies. And of course, as we've been talking about today, Spark uses aggressive caching of data in memory. So the thing to note here is that jobs are getting faster not just because they're doing less work, but because they're doing this work much more efficiently. They're using much more parallelism and they're storing data in memory such that they can still analyze gigabytes or terabytes of data, but they can return a result to the user in seconds or less. And then also, some folks are starting to use Spark for different workloads, like Spark Streaming, for instance, that analyze even smaller amounts of data such that the jobs can complete in hundreds of milliseconds or less. This is a trend that we expect to continue as we continue to improve Spark. So this is one trend, that jobs are getting shorter and shorter. And the second trend is that folks are using Spark on larger and larger clusters. You know, in the early days, we were using Spark on tens of machines, and now there are plenty of companies that are using Spark on hundreds of machines or more. The combination of these two things puts a lot more stress on the cluster scheduler. As tasks get shorter and shorter, the scheduler needs to make scheduling decisions more and more frequently because the rate of task turnover is much higher. And then, of course, as clusters are getting larger, the scheduler has more resources to manage. So to look particularly at the Spark scheduler, as of the 0.8 release, the Spark scheduler throughput was about 1,500 tasks per second. And if you start thinking about what this means, it places restrictions on how short of tasks you can run or on how large your cluster can be. So here I've shown a couple of different sort of packages of task duration and cluster sizes that the Spark scheduler can support for you. If you have long tasks that are, say, 10 seconds or more, the Spark scheduler can support a cluster of 100,000 16-core machines. So that's looking pretty okay for today's deployments. But as tasks get shorter, for example, if you want to run tasks that are 100 milliseconds, the Spark scheduler can only support a cluster with 10 16-core machines. So you can run a bigger cluster, but Spark will only on average be able to keep 10 of those machines fully utilized. So you can see that for the cutting edge of today's Spark workloads, the fact that the scheduler is this bottleneck and has limited throughput is starting to become an issue. Now, before I do anything too crazy and show you this distributed scheduler, I'm sure many of you are thinking, why don't we just try to optimize the Spark scheduler to improve this throughput? We've already done a bit of this. In the 0.8 release, we moved some of the code to support job monitoring and to support UI off of the critical path of the scheduler. This improved the scheduler throughput by a bit. And then in the 0.81 release, we also moved some of the code to deserialize task results off of the critical path. And this led to a 2 to 3x improvement in the scheduler throughput. There are a couple of other sort of low-hanging fruit type things that we can do to improve the scheduler throughput, but we're not going to get a 10 or 100x improvement in the throughput of the scheduler. We can maybe get 2 or 3 times higher throughput, but beyond that, we need to start thinking about a better design for what the scheduler is going to look like. So let's talk about how you can tell if the scheduler is the bottleneck in your cluster. The scheduler throughput is dependent on a couple of different parameters, like how many users are running. If you have more users, the scheduler needs to do more work to enforce fairness constraints, so the throughput is lower. And also, many folks don't know exactly what their workload is. But luckily, you can use the Spark UI to determine if the scheduler is the bottleneck in your environment. So in a couple of slides, I'm going to do a demo, and since the Wi-Fi is not working, there's a link to the UI at the bottom of this page if you want to poke around yourself. My Wi-Fi is not working, but I would encourage you to try it. So what happens when the scheduler is actually the bottleneck? There's this component in Spark called the cluster scheduler, and it's responsible for launching tasks on worker machines. When the worker machines finish the tasks, they send this message back to the scheduler. The scheduler notices that a worker's free, and it launches another task. And this process keeps going. But if you're trying to run tasks that are too short, or you're using a cluster that's larger than the Spark scheduler can handle, what will happen is that tasks will start queuing up at the scheduler. So there's worker machines that aren't in use because this message saying that a task is completed is still waiting to be processed at the scheduler. And the way that we measure if this is happening is that we measure the delay. We measure how long tasks actually spend waiting in this queue. And this is shown in the Spark UI. So my Wi-Fi isn't working, so we're going to have to sort of use our imagination a little bit here. But what I'm doing is I'm running, let's see. So this is the job that we'll see. We're running a job with 1,000 tasks, and each task just sleeps for 1 second. If we go look at what's going on the UI, I can't click around, but you can if you use that URL. What you can see here is that the duration of each task is 1 second, so that's what we would expect. And the scheduler delay here, this bottom row, is also quite low. At the median, it's 6 milliseconds. So everything is hunky-dory when we're running these long 1 second tasks. But then if we try and run a job that's composed of shorter tasks, so here I'm running a job that's composed of tasks that just sleep for 5 milliseconds, the scheduler delay is getting much longer. The median scheduler delay is 50 milliseconds. And you might be thinking, who cares, 50 milliseconds is a pretty short period of time. But if you think about the utilization in the cluster, what's happening is that for every 5 milliseconds of useful work that one of the workers does, it spends 50 milliseconds waiting for the next piece of work. So my 50 machine cluster is only 10% utilized here. On average of only 5 of the machines are actually being used. So this is actually pretty bad. But anyway, the takeaway here is not about this particular workload. It's just that if you're running Spark and you want to see how well the scheduler is doing, you can look at this metric, the scheduler delay. And if it's large at all, then you probably want to start thinking about using a different scheduler. So this is our diagram today of what Spark currently looks like, and there's the scheduling component that may be the bottleneck. What we envision the future of Spark looking like is that each user has their own Spark context. So each user does this query compilation on their own, and they also do scheduling totally independently. With Sparrow, we take this extreme viewpoint where we use schedulers that don't have any coordination, which has a lot of nice benefits. It has great throughput benefits. If you want to support a larger cluster or shorter tasks, you can just add more schedulers. And these new schedulers that you're adding, they don't need to coordinate at all with the existing schedulers that are already running. The second advantage is fault tolerance. If one of the schedulers fails, there's plenty of other ones. You no longer have this centralized point of failure. And the other nice thing here is that because each user can run their own scheduler, there's this nice fate sharing property. If the machine running the scheduler goes down, the user's machine has also gone down, so it's not such a big problem. Now, there's one missing part of this diagram, which is the storage, which was also one of the centralized components in the Spark context. And in this type of architecture, you need to be using Tachyon, which is a different project that I won't talk much more about, but there's lots of information about Tachyon available online. So let's dive a little deeper and look into how scheduling works with Sparrow. Spark submits a stage of tasks to Sparrow, where a stage has some number of tasks, and the scheduler's job is to place those tasks somewhere on the cluster. Now, what's different from the diagram before is that there may be a bunch of other schedulers running at the same time. They're also assigning tasks to machines, and this one scheduler has no idea where their schedulers are, where they've assigned tasks. It doesn't know anything about them. We'll use a queue on each worker. So if each worker is assigned more tasks than it has slots to run those tasks, it'll queue them up. Now, the big question here is, how can we possibly make this work? If there's no shared information, there's no global state about what's running where on the cluster, how can we possibly do a good job of assigning work to these machines? And it turns out that there's this very simple technique that Sparrow uses that works sort of amazingly well. So Sparrow uses this technique called batch sampling. And the idea of batch sampling is to use randomization, but to do a little bit of oversampling, such that we can throw out the most loaded worker machine, such that we can avoid sort of the worst case scenario. So when Sparrow needs to schedule a job here with 2 tasks, it sends 2 times the number of tasks of these lightweight probes to worker machines. So here Sparrow sends 4 of these probes to worker machines. And it chooses the worker machines completely randomly. Each of the workers replies with their current load. So the top worker here replies saying, I have a queue length of 3. And then Sparrow assigns the 2 tasks to the least loaded worker machines. So it turns out that this very simple technique provides great performance. But there's a couple of tricks that we need to do to make this work. And the most important trick, well, first let's talk about what the problem here is, which some of you may have already thought of, which is that queue length is not always a good predictor of the wait time. If you're running a heterogeneous workload, it may be the case that, for example, the scheduler probed one worker machine with queue length 2, one with queue length 1. It placed the task in the worker machine with a shorter queue. But it could be that those 2 tasks in the top worker were really short, the 1 task in the bottom worker was long, and the scheduler would have been better off if it had placed the task in the top worker machine. So this means that batch sampling, as I presented it before, won't work well if you're running a really heterogeneous workload. And to fix this, Sparrow uses a technique called late binding. And the idea of late binding is that we're going to wait to assign the tasks to worker machines until the workers are actually ready to run the task. So with late binding, again, Sparrow sends 4 probes to worker machines, but now the workers hold on to those probes. They keep the probes in the queue, and the Sparrow scheduler holds on to the tasks. Now we'll focus on the top worker here, and over time, that worker will process tasks, it will run tasks until eventually our probe is at the front of the queue. And only then does the worker machine request the task from the scheduler. So the assignment only happens when the worker is ready to run the task, and in doing so, we ensure that the tasks are placed on the worker machines where they'll run the soonest. Now, what about constraints? If you're familiar with the way that Spark works, typically the first phase of a job is constrained to operate on the machines where the input data lies. So here we have a stage with 2 different tasks, and the blue circle task should ideally run on one of the machines with the blue circle input data, and similarly for the pink triangle input task. Sparrow can handle these types of jobs with just a small tweak to the way that it does the sampling. Rather than sampling for the entire job, it samples individually for each task. So for the pink triangle task, it randomly picks 2 of the machines that satisfy that particular constraint, and same thing for the blue circle task. So to summarize, I've presented this very simple technique that Sparrow uses based on randomization called batch sampling. I've demonstrated how Sparrow can use late binding to avoid problems with predicting the queue length on worker machines, and finally demonstrated how Sparrow handles constraints. Now, how well does this thing actually work? First, we compare Sparrow to Spark's native scheduler. So what we're doing here is we're running jobs that have 10 tasks where all of the tasks are the same length. This is in a cluster with 100 machines. On the x-axis, we're decreasing the task duration, and as we do that, we expect the job duration to correspondingly get shorter. If you have 10 tasks that are each 1 second, your job should finish in 1 second. That's what's shown by the black dashed line on the graph. What you can see is that Sparrow follows that ideal line almost perfectly, whereas the Spark native scheduler, once tasks cross this threshold of 1.5 seconds or so, the tasks start experiencing infinite queuing, and as a result, the job response time climbs to infinity. Now, it's nice to see that Sparrow does better than the Spark scheduler, but we'd also like to get a sense of how it does in an absolute sense, and also how it does on a more realistic workload. This is a synthetic workload where all of the tasks are the same length. So to evaluate that, we ran the TPC-H benchmark on Sparrow. And we did this using Shark, which, as many of you may know, is a SQL analytics engine that runs on top of Spark. So this graph shows the response time of 4 different TPC-H queries. And what you're looking at is various percentiles with Sparrow. Those are the purple boxes. And we're comparing Sparrow to 2 alternatives. The red box is what would happen if we just randomly assigned tasks to worker machines. And as you might guess, random assignment does quite poorly. Sparrow does many times better than just randomly assigning tasks to worker machines. But what's really cool here is the comparison between Sparrow and the ideal box. So what's happening in the ideal box is that's how long it would take to run these tasks on a completely idle cluster, and if there were no scheduler delay. So we're removing all of the time that the scheduler takes to make a decision, to ship the task to the worker machine. Even compared to this aggressive optimal, Sparrow does quite well. The median is within 12% of the ideal scheduler, and Sparrow has a median queuing delay of just 9 milliseconds. So with this very simple distributed technique, we're able to do almost as well as an ideal scheduler. Now, there are a couple of more things that are important in actually running a scheduler on a cluster, and one of those things is doing policy enforcement. You may want to enforce strict priorities, where certain users' jobs are always run before other users, or do some kind of fair sharing. Sparrow can also support this type of policy, and the way Sparrow does so is by maintaining multiple queues on worker machines. So instead of just having one queue of probes, Sparrow keeps multiple queues of probes with one for each policy group. So one for each priority and the priority scheme, and one for each user in the fair sharing scheme. That when workers are applying to probes, they serve the queues based on the particular policy. So for fair sharing, for instance, Sparrow would serve the queues based on weighted fair sharing. Now, you can see that we're giving up a little bit here. We no longer have global visibility, so instead we're doing this policy enforcement on each worker machine, and as a result, we won't get perfectly accurate policy enforcement. In the priority case, for instance, you might have all of your high priority tasks queued on the same sort of subset of worker machines, so they won't get run immediately. But it turns out that this actually works pretty well. So here what we're looking at is a case where you have 2 users running in a 100 machine cluster. User 0 has an infinite backlog of work for the scheduler, and user 1 increases the number of tasks that she's submitting to the scheduler every 10 seconds, or sorry, rather changes it every 10 seconds. And both users are given equal share here. So at 10 seconds into the experiment, user 1 increases her demand so that she has 100 tasks ready to be run at each point in time, and then the same thing at 20 seconds in. What you can see here is that there's very small oscillations around the fair share, and this is due to the fact that we're doing this distributed enforcement, but it works almost perfectly. It works well enough that no one would ever be able to notice, for example, that they had 98 tasks running instead of 100 or something like that. Now, the final property of Sparrow that's very useful is the fault tolerance property. So what we did in this experiment was we had 2 different Spark clients that are both initially connected to a Sparrow scheduler, but we also initialized each client with a list of backup schedulers to use if their scheduler failed. At 20 seconds into the experiment, we kill the scheduler running alongside the first Spark client. The Spark client just uses a simple timeout to detect the failure, which happens within 100 seconds. 100 milliseconds, sorry. In 5 milliseconds, the Spark client fails over to the second scheduler, and within 15 milliseconds, it's able to resubmit all of the outstanding queries. So this entire process of failover happens in only 200 milliseconds, and it happens so quickly that only 2 queries were in flight during the failure. So only 2 queries are affected by this failure, and we're able to fail over quite quickly. Now, Sparrow's not quite feature complete with the Spark scheduler yet. There's a couple of things that it doesn't do. One is that it unfortunately does not yet interface with the UI that Patrick had talked about earlier. A second problem is that Sparrow doesn't currently do delay scheduling, and it also doesn't do speculation. None of these things are going to be huge to add, and we're planning on adding them in the short term. If these are things that you're interested in, we would also love to work with you to help us get some of these last things done. Just to summarize, what I've talked about in this talk is the Spark scheduling bottleneck and how you can detect it using the Spark UI. Then I've presented the simple distributed technique that Sparrow uses to provide high throughput and fault-tolerant scheduling, and I've demonstrated that it actually works quite well, that even without global visibility, Sparrow can provide almost optimal performance. So with that, I'm happy to take any questions.
Hi, very cool stuff. But it's given the fault tolerance benefit, it's reasonable to think that someone might want to migrate on this, on a cluster that isn't necessarily thousands of machines. And in such a case, right, the number of tasks might outnumber the number of cores. So in that case, it seems like batch sampling essentially is a moot point, right? Because you have more tasks than you can't oversample essentially. So how much benefit do you still get simply by sort of this optimized queuing with the probing method? So I mean, because you see these throughput benefits, but without the over or the batch sampling, I mean, does it still seem to perform well?
Yeah, so I think you're right that your question is, just to repeat the question, that when you have a situation where there are more tasks than cores, you can't really do this oversampling. And you're exactly right.
Well, so I mean, there's two aspects to the optimization, right? So this whole probing thing where you can prioritize nodes, right? So you might, in certain cases, certain workers are burning through tasks much quicker than others, right? So your task might go to a subset of workers. So how much does that half of the optimization improve the throughput, right? So there's these two parts here. I'm kind of curious as to how each, affects the overall performance.
So how each affects the performance when you have more tasks than worker machines?
Yes.
Yeah, so when you have more tasks than worker machines, there's really no point in either of these things. Like, what you would want to do is just short circuit the probing mechanism and just send the tasks straight to the workers, because you're going to use all of them anyway.
Last question. I have written my first cluster scheduler like 12 years ago, so I can fully appreciate the awesome work you guys done there. The question I have: do you have any comparative benchmarking between Sparrow, Spark scheduler, and other application schedulers in the big data space, by any chance?
Yeah, so when we started this project, we were targeting these low latency workloads, these workloads that were running jobs with tasks that take on the order of hundreds of milliseconds to complete. And none of the other cluster schedulers that we're aware of target this same environment. So just to name a couple, like Yarn and Mesos, for example, both start a new container when you have a new task to run, which involves launching a new JVM, which takes on the order of seconds. So it doesn't make sense to use something like this when you're trying to do scheduling on the order of magnitude of 100 milliseconds, because launching the container is going to take 10 times as long as the task itself. There's a couple of other schedulers in this space that target this finer grain task scheduling. Like, one is Quincy, which is the newer Dryad scheduler built by Microsoft. Quincy does this sophisticated optimization that is able to satisfy much more complicated placement policies. Like, they're able to do optimization to put tasks where the network communication will be minimized. But as a result, doing an assignment for a machine with for a cluster with 1,000 machines takes on the order of a couple of seconds. So again, it's really too long for these short workloads.
Okay, let's thank Kay again.